Thank you so much, Kunal. Thank you so much, Professor Wong, for that very fascinating talk on a topic that affects us all or will likely affect us all in the near future. I'm reminded of a poem that I studied in my high school English literature, Water, Water Everywhere, and Not a Drop to Drink. But it's very promising to see that in the near future, a lot of efforts are being done to ensure that we'll have water everywhere and also drops to drink for everyone. With that, I'll begin taking up questions from the audience. And it goes without saying that we have a lot of accolades for you in terms of questions, in terms of the reactions and the thumbs up. The audience also mentioned that they really appreciate and like the slides. So thank you so much for all that. So the first question is about, the feasibility of implementing solar-powered desalination or solar-driven water production systems. How far are we from implementing these? Let's say on a large scale in developing countries that are struggling with water scarcity, for example, India.
All right. So that's very very important question that we have been asked for many times. So there are different ways of utilizing solar energy to do the water desalination. So our design is one. Now, a more conventional solar-driven desalination is that the electricity is generated by solar energy, and that electricity is utilized to drive conventional reverse osmosis or MSF type of thermal-based desalination. So our approach of utilizing the heat produced by the PV panel to drive the membrane distillation type of the desalination, I would say it's it's suitable at small scale application, small to medium scale application. So it's suited, as I indicated in my title, for decentralized drinking water and even decentralized electricity production, because in our system, there's no high pressure involved. There's no mechanical part. There's no vacuum that is being involved. So, from this point of view, our goal is the same as many of our audience. So they should be utilized at decentralized scale for point of consumption purpose. However, having said that, we are not at that point yet. All right. So we are still working on 1/8, 1/4 of the commercial PV panel size. We have at this point many engineering challenges that we have to solve before we can say that they are ready to be deployed for real application. Yeah, so that's my general answer to this. I'm not sure if I really answered the question.
Thank you, Professor Wong. I'm sure the researchers are taking notes and perhaps being inspired by the research issues that lie ahead before these, solar power desalination units are being implemented on a large scale. So with that, moving on to the next question, you shared about some fancy materials. So do you think that MXenes, apart from titanium carbide, which is commonly used, these materials have the potential and the economic viability to be used for desalination or water production applications?
All right. So I will say there two potential application area for MXene. All right. So in my talk, I introduced MXene as a photothermal material. Right, that's one, because it can convert solar energy to produce heat. You're using that heat to do thermal-based desalination. And then, since this is two-dimensional, right, two-dimensional nanomaterial, there has been report that incorporated MXene into conventional, RO membrane, nanofiltration membrane, or even use MXene to make all inorganic membrane for desalination or other application. All right. So for the thermal material with MXene, I would still gonna repeat what I presented in my talk, unless you see a special benefit from using this very fancy material, right? I don't see any benefit of using more expensive material than very conventional carbon-based material like a carbon black, because I don't see any difference in terms of the solar to heat conversion efficiency. All right, for the second part, at this point, second part is on utilize MXene as membrane, additive or membrane material. It has been studied for a while, and also I'm not a real expert in this field. I'm gonna, I'm gonna try not to, give some misleading answer to this question. So let's wait and see.
Thank you so much, Professor Wang. So fancy may not always translate to being a better material, as you shared. So Professor Wang, we understand that it's already close to 7 and it's a bit too late for you, but we wanted to check if it would be all right if you could stay with us just for a few minutes longer so that we could take few more questions from the audience. Thank you so much.
Absolutely, absolutely.
So the next question is about a challenge that's associated with such systems. It's actually the low evaporation rate. So an audience member wants to know whether they can use some kind of optical assembly, let's say a combination of optical lenses in conjunction with a solar distillation unit to increase the evaporation rate. And would this also impact the stability of the photothermal material?
That's a very good question. All right. So my personal opinion on this is this: when you evaluate the applicability of such a system, we at this point look at the production cost of this system very carefully. All right. So if with the concentrated solar light by utilizing lens assembly, you can justify the water production costs. I think you definitely go for that, but most likely, with this highly concentrated solar light, system to produce, concentrated solar light, the energy efficiency of the entire system might be less. So it's counterproductive based on my general understanding to such a system. Now, I do have reasons why. So with concentrated solar light, you increase the evaporation temperature very significant. Now, high evaporation temperature requires in this system a very good thermal insulation design. Otherwise, remember, an object with high temperature will tend to emit infrared, all right, with high intensity to the outside. That's considered as energy loss, right? So when you want to do the concentrated solar light, you have to think about the energy balance very carefully. All right. So I'm not quite sure what is in your mind when you ask this question, but so long as you do a thermal balance calculation before making your decision, I think you will be on the right direction for sure.
Thank you, Professor Wang. So the next question is about the challenges associated with incrustations and how such issues are managed in the photovoltaic evaporator devices.
Can you repeat the question again?
So how incrustations such as dirt or a chemical, they are managed in the photovoltaic evaporator devices?
All right. I'm trying to understand what is the meaning of that.
Perhaps it's, I mean, to be honest, we just Googled. We were also not aware. It's a layer of a material such as a dirt or a chemical that forms on something. So we're guessing that such materials would be used in arid regions where there might be dust, so, or dirt.
All right, so I can try to answer the dust issue because that's something we have been thinking about for a very long time. Now, with the atmospheric water harvesting, you can produce a small amount of very precious fresh water in the middle of desert. That's where we typically set up large-scale PV farms. All right. Now, dust is a big concern with those PV farms in the middle of the desert or in semi-dry, semi-arid area. Because when you have a layer of dust on top of the PV panel, the energy conversion efficiency can be easily reduced by 50%. So cleaning of the surface dust of PV panel is actually essential, but it's very challenging because you don't have access to fresh water in those regions. Now, our belief is this: since we can produce small amount of fresh water from dry air by using our solvent, all right? You can use small amount of water to produce some crop. You can use the rest amount of the fresh water to do the often PV panel surface cleaning or desoiling. With this, this small amount of fresh water produced from nowhere can really make a big difference in terms of the keeping the amount of electricity generated by those PV panels. So we have been thinking about this. We are trying to make a system that is smart enough so that when the water is being produced, the system can actually divert water to the top of the PV panel, so the whole process can be automated. But we are not there yet.
Thank you, Professor Wang. So the next question is about the quality of the input or raw water. So what was the quality of the input or raw water used in the membrane distillation process? And is there any pre-treatment that is required? And
So,
additionally, yes.
that's very very critical and professional question. I guess this guy who asked this question did some membrane membrane distillation based desalination him or herself. So I can tell you, in our system, we use real seawater directly, and we did not treat the real seawater with any chemical. The only thing we did was to the laboratory filtration regular paper. So we used that paper and we did a simple filtration. That's what we did. And very surprisingly, within this specially designed multi-stage membrane distillation system I reported here, the whole system can could go on for a very long time without any membrane fouling issue. So the reason is something we are still working on. But yeah, so we did not add any special chemical for this membrane distillation experiment in our experiments. We did use the real seawater.
Thank you, Professor Wang. And in addition to real seawater, can we also use produced water, let's say shale wastewater or oil industry wastewater as the input to produce potable water?
The answer for me is absolutely no. All right. So membrane distillation-based process has a bottleneck. All right. It works with the raw water that has low concentration of volatile organic compound. Otherwise, those chemicals will be evaporated along with water and go through the membrane distillation membrane and be condensed on the other side. They will be part of your fresh water, which is something you do not want to have. Therefore, co-produced water or produced water is not suitable for this design to produce fresh water.
Okay, thank you, Professor Wong. So next question is about membranes and what kind of membranes are used for membrane distillation applications. Is there any specification on the porosity, chemical structure, or their hydrophobicity, philicity, etc.?
That's also a very good question. Generally speaking, so long as you have the regular membrane distillation membrane, it should work. It should work. But for our latest design, where our system was able to cool down PV panel. So in doing that work, we realized so long as you can modulate the property, the thickness, the porosity of the membrane, you can use the system to cool down the PV panel on the top. So in that sense, those physical chemical property of the membrane is very crucial so long as you want to have higher energy efficiency.
Thank you, Professor Wong. So we'll just take one more question. Although we do have a lot more questions, but we also want to be mindful of your time. So water treatment seems to be a great option at present, but what about the concentrated waste or brine that might be produced after the process? And how does that impact the water budget and its distribution in different reservoirs?
So I think I missed the first part. What about the
concentrated waste or the brine that might be produced after the process?
Yeah, so my third topic, all right, the third topic of my talk, touch upon this briefly. So far, based on, I think, majorly financial consideration, the many industrial processes, many large desalination plants, they do have the technology to treat the brine, but they choose not to because the electricity consumption by such a process is massive. It's really massive. So I did some calculation myself. So if Saudi Arabia at this point wants to treat all of its desalination produced brine towards zero liquid discharge, all right? So more than 50% of the electricity generated within the entire country will be consumed by this single process. It's not affordable. So how to develop brine treatment with zero liquid discharge that is low carbon, that is less electricity consumption is something that many people are working on, but still this research topic needs more, especially younger generation to be part of it.
Thank you so much, Professor Wong, for your time and for your patience in answering all of these questions. We still have a few more, so if it would be all right, we would perhaps share these questions with you via email and share your answers back again with the audience members. And a large fraction of the audience has actually stayed back with us, even though it's beyond 7. So this goes on to show how interested and fascinating they found this topic today. If you could just share one concluding remark with the audience members and the young researchers who have joined us today.
All right, I want to say to our audience that the global warming creates a lot of challenges, but I also want to say it also produces a lot of opportunities for you guys, because you are the future of the world. So work hard, work together. We can solve those grand challenges of our time. So let's work together.
Thank you, Professor Wang. I think that's a wonderful way and a positive way to end the session for today. And thank you so much for hanging around for a little while with us. So this brings us to the end of today's session. We hope that all of you have enjoyed this broadcast. We invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy.